Welcome to module number 3, that is a frequency and voltage control, and today just I'll be discussing the basic introductory part of the frequency and voltage controls. This is the first lecture in which I'll discuss first the frequency control and then some salient points about the voltage control. To see this frequency control, although in the power system there are so many things are controllable, we can control, but in majority that's normally we control the voltage and frequency by controlling other of the generators, load and other devices in the system. Frequency is very important and vital along with the voltage, as we know for the efficient and secure operation of power system we should have certain objective, and those objectives are that we should maintain the reliability of the system, we should have security of the system, our system must be stable, and we must operate the power system in the most economical way. Along with that, we must provide the power to the customers with the better quality of the supply. In terms of quality, normally we relate, earlier we were talking about the frequency and the voltage, that we should have the frequency limit, that is here there is a plus minus 3% that we can vary the frequency. However, the voltage control, we can even though go for plus minus 10% of the nominal or rated value. This 10% basically for the low voltage side, low voltage. However, it is a requirement for the various operating apparatus or devices in power system that we should very closely operate, that the voltage should not exceed than plus minus 5% here for high voltage system. Now in the frequency, as you know, this frequency is a global phenomena, means the frequency throughout the system is the same. Means if you are measuring frequency at one end of the system and you are measuring the same time another end of the system, the frequency will be the same. However, the voltage is a local phenomena, and the voltage at one point here it will keep on changing. Means if you are at one point it will be different, another point it can be also different. So the voltage is a local control, local phenomena, and the frequency is the global phenomena. Now the question here, why we want the so rigid about that plus minus 3%? What is harm to operate beyond this limit, or we can go for any 10 or 20%? To the application of the frequency control, you can see the several devices, several elements, apparatus, they are operating on the very controlled frequency range. For example, you can see the electric clocks. They are basically measuring the frequency of the AC supply, and based on that it is set. So if the frequency of the supply is changing, the clock which will be giving the timing, that will be also changed. Nowadays the modern control apparatus, or you can say apparatus, or you can say consumers, utensils, appliances, they are also very much affected by the control, and they are using the sinusoidal frequency, and that frequency is used to control these devices. So if you are changing this, even though there are so many computerized control machines, CNC machines are there, they also work on the system supply frequency. So if the supply frequency changes, then whole control process will be changed. So in the modern age, we must operate our system very closely to its rated value. Again, the frequency, we know in all over the world we are having two type of frequencies, two level of, you can say. One is your 50 hertz and another is your 60 hertz. 60 hertz basically it is used in the USA and Canada area. However, the 50 hertz is used in Europe, Asia and the most other countries. So we have to, this nominal frequency, just we are talking here plus minus 3%. It is in our case, in Indian case, it is a, just we can, means we should operate our frequency range with 48.5 hertz to here 51.5 hertz. But normally the frequency sometimes even though go below that, and that is not good for the system operation. Now if you are, again, if frequency is less, no doubt apart from that's a requirement for the electric clocks, for the control units, along with other requirements, if you are still operating below that, then it may create the system stress, and that may again give your poor reliability of the system, and also your system may not be stable, and it is very verge of collapse. So always our intention is to operate in the plus minus 3%. This frequency can be controlled by two way. Here you can see this active power control is possible at the generation and the load level. This frequency basically, it is directly here is related to the frequency, and that is throughout the system. So to control the frequency, we must control the real power or active power. And the active power in whole system, only we have the two sort of controls, means we are injecting the power through alternators and we are consuming power through the loads. So we can have a complete power system. Here, let's suppose your system is there. Here we are having various generators. So these generators are injecting the power, that is the real power we are talking. And here the various customers are there, they are taking the load. So this is the generation bus, this is your load bus. Similarly, we may have other generators, they all are injecting power into the system, and the customers here, they are taking power from the system. So these two subcategories, means generation and the loads, they are responsible for the system frequency. So if you want to change the frequency, we have to change here the real power output of the alternators or real power consumption of your loads. So that's why here I have mentioned this active power. Now active power we can control, that is possible only at the generation and at the load levels. So it is preferred to control the power at the generation side. Load and control is done during the emergency. Suppose your system frequency here, if here the system frequency which was operating that F0, that is a nominal or rated, or it is a 50 Hertz in our case. So if this frequency, you can say this frequency falls, means if this frequency decreases, the options are with us that we have to increase the power. The fall in the frequency directly shows that we have the deficit of power in the system. Means your supply as well as the load is not balanced. Means you are having limited generation and you are consuming more, so that's why your frequency is falling. Why it is so? You can understand again with this, that if your generation, total generation I am talking, generation of all the generating stations, if you are adding together, that is greater than your total demand or load, then your frequency will rise. And if your total generation is less than your total demand or load, frequency will fall. Now why it is so? In the previous module, I discussed about the swing equation, and you know it here that I can write here this angular momentum. Here I can write d omega upon dt, that is a rate change of angular frequency. Here I can go for here Tm minus Te. So this is your power which is we are injecting, that is the input. Here this is the electrical power, is the output. So what will happen if this is imbalance? If there is acceleration, or this is also called the TA, accelerating torque or accelerating power, if you can convert the unit in per unit, both are same. So if this is positive, then your speed will rise, and if this is negative, then this speed will fall. So in other words, what is happening, if your power generation here, the total power generation, that is a summation, if it is more than your P demand, total demand, what happens? We have the surplus power, and using the energy conservation theorem, that energy cannot go anywhere, so that energy is stored in rotating mass in the system. And the rotating mass is, rotating mass energy is nothing but it is a kinetic energy, and that kinetic energy is increasing, means we are increasing the speed of the system. So if this is more than your demand, then the frequency of the system will rise. And reverse is also true, that if your this P generation is less than here than your demand, then what happens? You are drawing more power than your input. So you have the energy deficit. So what happens? That more demand, less generation, means the demand which is required here, more excess, is met from the kinetic energy stored in the system, and therefore the frequency of the system will fall, because the kinetic energy is reducing, means is a reduction in the speed, and then therefore it is a frequency. So this is true that here if the total generation is more than total load or demand, load here is basically nothing but it is a demand, frequency will rise. If your total generation is less than your demand, then frequency will fall. So the real power, which is main source to control the frequency of the system. However, this reactive power means we have the two powers in the system, that is real as well as the reactive. Or alternator or a generator can generate real as well as the reactive powers, and load can consume real and reactive powers again. So the reactive power control is responsible mainly for the voltage control, which is a local problem. So this is your load frequency control. Now how we can control the loads? Again, to understand the load frequency control, if you can see a system, the generators, if they are connected into the complete system. So to understand here, a generator can be connected with the rest of the system where the several generators are operating. So it is called the interconnected system, where the various generators are operating in the parallel. There is also possibility that single generator is feeding to the isolated load, and it is normally called the generator which is operating in the isolated mode. So the frequency variation, if it is in isolated mode, is not of the great concern, because if it is delivering the power. But if it is connected with the rest of the system where the various generators are there and they are operating in the parallel, various generators, so the frequency is very much regulated. To understand here, let us suppose here the characteristic, normally all the generators are equipped with the speed governing system. So here, if this axis is your load, where if you are changing the load, what will be your here speed, and speed is directly related with the frequency of the system. So here this characteristic, normally here it is a just falling characteristic, that if your load is here, let's suppose here the 25%, here it is a 50%. Now if we are here is 100%, at this point it is, let's suppose, 99% of the speed, here it is 98%. So if your load is increased from the no load to the load, the frequency of the here the system will fall. The frequency of your generator will fall. So you can see by increasing here the 25% or 50%, frequency is going down. Then what happens? The governor will try to lift, to increase the speed by increasing the prime mover input, and finally will settle to the frequency. So there is some control, and normally it is a closed loop control. I will discuss about the detail about the closed loop controls. There are various levels of controls are there, and it will try to raise the frequency and try to maintain at its rated value, that is a nominal value, or you can say the 50 Hertz in our case. Now the load frequency problem, again let us see what are the various type of frequency control that we can categorize. Let us suppose we have two generators here, and these generators are connected with the tie line here, and they are having the loads and feeding to the its own area. Let's suppose this is your S1, this is your S2 generator, and these are the loads. Here you can say load, here it is also load. Now if there is any change in the loads either at this substation S1 or S2, if only one generator, let us say the S1 is responsible to control, to meet that demand, means here if load is increased, the system frequency will fall. Then if this S1 will try to increase its generation, as I said, we have to meet the demand, means always your total generation here will be equal to your total load or demand. So if the load here at the generating station 1, here is 2 or 1 if it is increasing, and only one generator is responsible for maintaining or to taking care of that load increase, then it is called nothing but it is your flat frequency regulation. So it is called flat frequency regulation. The main advantage of this is key, that here whatever the load is changing, we are operating now S2. Let's suppose S1 is taking care of the load change. So S2 is operating at the base operating. There is a possibility if this S2 is very cheap, then it should keep on operating its maximum value, and those are the expensive generator. For example, if S1, then it should change its output to meet its demand. So then we can have the economical operation in this sense. But the problem here, That's only all the load here that is changing. It is met by S1, and there is a huge excursion and huge loading that is coming on S1. So both advantage and disadvantage of these schemes are there. Now other possibility is that if the load is changing anywhere and both generators, let's suppose the load at here it is changing, so both generators are taking care of that increase, and this type of operation is called the parallel frequency regulation. So this is called parallel frequency regulation. The third type of possibility is that how we can control that if load change is occurring here, then only S1 is responsible, means the load change in any particular area is met by the generator in that area itself. Means if load change here, then S1 is responsible. If load change here in the area 2, then S2 is responsible. Then it is called another type of frequency, and this is called flat tie line loading. What does it mean? It means that here the tie line power is maintained fixed. It is not changing. However, in this, you can say a flat frequency regulation, if load here is changing and S1 is changing, then the tie line power is also changing. So is a tie line power is not flat, it is keep on changing. No doubt if the load is increasing here and this generator is changing, then there is no change. But since this generator is taking care of the load change in the both area, both the generator, so it is a flat frequency. Here in the flat tie line, we are maintaining the tie line power flow here constant, and the load change in particular generation area is maintained, is taken care by that particular generator itself. And here if changing in S2 zone, then S2 is taking care. So in normal way, if the two big areas are connected by tie lines, normally we try to maintain the tie line power to its scheduled value unless until there is some disturbance in any particular area. If any one of area is in an emergency state, so then he can request and we can feed more power, and then we can stabilize both of the system. But in the normal practice, what happens, it is not only one generator, most of the generators, they are taking care, and now parallel frequency regulation is very, very prominent. Means all the generators are changing their outputs to control the demand of the system and try to maintain the frequency. So this is called your parallel frequency regulation. Now here it is clear that to control the frequency, we must utilize the control aspect of the alternators or governors. As I said in the beginning, that we have the two possibility to control frequency. One is your generator output, and second one is your load aspect. Means if your frequency is higher, means let's suppose your frequency, operating frequency, here it is more, I can say more than your nominal frequency F0, then you have to, what does that mean? That the operating frequency is higher, means your load is less and your generation is higher. So the possibility that you can reduce this generator outputs and then you can match the demand and you can reduce the frequency. Another option that you can increase the load and then again you can meet the balance between generation and load. Now the load increase, it is not in your hand. It is very, very difficult to increase the load unless until you are saying to somebody, can you increase, can you take more load? But normally it is not in the practice. Load increase is not possible. So what we do, we try to ask the generators to reduce the output to maintain the frequency to its rated value. Similarly, if your frequency of operation is less than your nominal frequency, that is F0, or rated frequency, that is the operating frequency of the system, which is 50 Hz in our case, this shows that your generation here, means your generation is less than your demand. So what we can do now, here instead of going for the reduction in generation, we can here increase the generation or we can go for reduction in the load. So the reduction in load that can be done. We can use the under frequency relays, and then if frequency falls down to its set value, it will try to set several loads. It will try to set the feeders, switch off the feeders, and the huge amount of load will be released and the system frequency will be restored. But this option is again very expensive. Normally it is not used. So we try to increase the generation to take care of the frequency. So normally we go for the generation control, and the generators are equipped with the governors. So we will see here how the governors are working. So the generator control loops here. In the generators, normally we have the two loops. Again, I'll describe. One is the control to the turbine input, and the inputs are your steams, gas, or it is water. And here this load frequency or generation control loops are known as load frequency control. Basically in the literature you will find that different names are used, but the purpose here is to control the frequency of the system. So it is also known as load frequency control. Normally it is called LFC problem. Or it can be called as automatic generation control. AGC is also very popular, and sometimes people call it automatic load frequency control, ALFC, or here we can call it some megawatt frequency control loop, because we are changing the megawatt, frequency is changing. So we can say megawatt frequency loop. Another control loop in the generating stations which are equipped with, that is called the excitation control, and that excitation control is related with the control of the voltage of the power system. So the excitation control is also known as the MVR, because we are controlling the reactive power with the help of excitation, and what we are achieving? Zero voltage. So it is called QV control. This is very fast because there is no rotating part. However, the control here, that is the ALFC, or you can say LFC or AGC, that is a frequency control, it is slow process, because we are the turbine inputs, and turbine is a mechanical device, and then mechanical device is rotating, it is coupled with alternator, and then your electrical power output is coming out. So the dynamics of time constants of turbine, the steam pipes, steam flowing, as well as the alternator accounted for. So this is the slow. However, this excitation control is very, very fast, because only we are having the exciters, and they are maybe static exciters and no rotating part, so it is very fast. So in steady state, these are basically non-interactive loops, means they are not interacting to each other. Both loops are separate. But during the transient or emergency conditions, they also work together, and voltage, because voltage is also related with the power, it's not only with the Q. So in that case, here both loops are interactive. But in the normal steady state, here both loops are non-interactive. To see here, now see the various control loops. Now what we have, this is your alternator. This alternator basically is coupled with the turbine. Again, there will be the several stages of turbines depending upon the output rating of your alternator. If you are using 500 megawatt alternator, then there are 3 turbines. One is called your high pressure, intermediate pressure, and the low pressure turbines. So there are 3 stages of turbines. So all these 3 stages here, it is coupled, and it is written here in the turbine system. So this turbine system is a mechanical rotating device. The input to this is coming here, your steam, and since you can say there is an expansion of the steam, so work done here by this turbine on the system, the turbine will try to rotate, and it will here try to rotate the system complete mass, and then alternator is now will be rotating with help of turbine shaft, and finally it will be giving here the power output, that is P. So what is happening? Now to change the speed, we have to change the input flow here to the turbine, and that input is steam in the thermal power stations, gas maybe in the gas power station, and the water in case of the hydropower station. So to control this, now we have to measure the speed of the system. here we can measure the frequency of the system. Here we are measuring the speed with the sensor, and this omega is coming. This omega is basically compared with its reference setting speed, and if there is any change, then we are getting an input signal that is change in omega. It's not W, basically it is omega, that is a speed, and then speed is basically coming here, that is a power frequency controller, and this power frequency controller here is changing to the valve control unit, and this unit will try to change its input to this here turbine, means it will try to open and close depending upon the requirement. Means if your speed is higher, what it will do, it will here, this value will be positive, this controller will try to close the input to this turbine, means will try to reduce the steam which is passing through the turbine. So here mechanical power is reduced, and finally the speed will be settled down to its rated value. In other words, if frequency is less or speed is less, then here this will try to open more and more steam will pass, so that we can increase the mechanical input to this turbine. Another sense that we can go far, here we can sense the frequency of the system, that is here we are sensing the frequency. So we can measure the frequency of the system, that is here it is generating three-phase supply system. So frequency is measured, and this frequency is now compared with the reference setting, that is a rated, or you can say here F0 of the system supply. So if there is any discrepancy, mismatch in the measured frequency and the reference value, so then we are getting another signal, and that signal is also coming to the PF controller. So we have here this control is basically called the real power frequency control loop. So you can say this is a loop, here this is a loop. Now another point here, just normally it is equipped, it is not only with relation to the frequency. Sometimes utility want to increase the power irrespective of the system frequency, means they want to control, that is called the manual control. These are the basically automatic taking care. So if you want to change the output alternator manually, then we can change here, and that is called power controller. So if you want to increase the power, then here your desired here, what is actually coming, that we can measure here the power output, that if you want to change your output level and there is some difference, then it is also coming to this PF controller, and then it will try to do this. So here we have the automatic as well as the manual. Normally it is called the raise command. We'll again see and model the governing system. So this is basically related with the governor. Valve control is nothing but there are some governor systems. Means we have to try to move this here, it is movement of this system, so that the input to the turbine can be changed. So this whole system here which I discussed up in this boundary, here it is your called the real power frequency control, or it is called LFC control, or ALFC control, or it is your AGC, and so on and so forth. Another control loop is that we have here, you can see we are sensing the voltage. This supply voltage is sensed, so we are measuring the voltage of the system, and now we are using a comparator to compare with its reference value. So normally the terminal voltage of alternators are set at the pre-specified value. It may be 1 per unit, it may be sometimes it is more than 1 per unit, and if there is some here error signal is there, means change in voltage is required, then your QB controller will act, and it will try to change the excitation system, and so that we can change the excitation of this alternator, and that will try to change the terminal voltage of alternator. So this loop here, it is called your QV loop, or sometimes called this MVAR, voltage control loop. So now let us see how we can achieve this active power control. So in this load frequency control loops, we have three major parts. One is your speed governing system, means speed governor normally it is called. Another is your rotating component, and that component basically consists of your turbine and the generators. Those are rotating because it is related with the mechanical rotation, and we have also the load and the power system. So we have these three major components that we can classify. Here the load frequency control loop in the speed governing system, rotating components, that is your turbine and the generator, and we have the load and the power system, that is a electrical part. So here this is a mechanical, so we have to model the turbine and generator combined together, that is the rotating components. Then we should have your speed governing mechanism and its characteristic, its modeling, and then we will also model the load as well as the power system together, and then we can analyze that control loops and we will see the load frequency control loops, how they are working. Now in the speed governing system, or you can say turbine speed governing system, that is same, it is consisting of four parts. First one is your flyball speed governor system, hydraulic amplifier, speed changers, and various linkage arrangements are there. To see it, you can see this diagram. This is basically the simplified functional diagram of primary ALFC. I'll come to the later part why it is primary. I'll mention later on, because there are primary and secondary control loops, and here it is called automatic load frequency control loop. To understand here, as I said, main purpose here to change the frequency, that we have to change the mechanical input to the turbine, and that can be changed by here closing or opening of this valve. Means if this is closed, steam is passing less, mechanical input is reduced, and the frequency of the system will increase. So here we have to only just input, that is called to the turbine, which is going, we are changing this one, that is a input to the turbines. And for that we have the various mechanisms. One that is called the speed governing mechanism. Here you can see, and that is what we are doing. We are measuring the speed, and this arrangement is called your flyball speed governor. What happens here, if your speed is more, here speed is going to be more, what will happen? This value will change, and finally the movement of B will occur. I'll come to that. Whether this B will increase or reduce, we'll see later. But if your speed here is changing from the base case, the movement of this B will be changing depending upon the more speed or less speed, and then by this mechanism here, this movement here will be changing. Another arrangement, as I said, that we have another, that is a manual control. Means we can intensely increase or reduce the power output of alternators irrespective of the system frequency, and by that we can have here this lower and the raise commands. Means if you want to increase the power, you have to, for here raise, if this value is shifting down, means your position of A is going down, that is here called change in the P ref, then power will be increasing. How it will be? It is functional. To understand this, let us that we are going to increase the, here just we are giving the raise command, means just we are trying to increase the output of this here turbine output, means we are increasing the steam which is passing to the turbine. So here, and this mechanism is called your speed changer. So if you want to increase, let us see that I want to change the frequency, I want to change the power increase, means by the raise command, we are not concerning about the here change here. What will happen? The position of A will go down, or we can say the change in XA position is, that is directly related with the change in the power reference that you are changing. So if this is going down, this is if B is a constant, we are not changing this B, what will happen? The position of this C will go up. If this will, you can say this is a linkage mechanism. If this A is coming down, C will go up if this B is constant. So what will happen if this will go up? Now you can see if this is going up, your XD here will also go up. If this XD will go up, here we are just putting a high pressure aisle. Here you can see the high pressure aisle is coming, and this is going up, then the direction of this aisle will flow like this, and it will try to flow here. So what will happen? It will try to insert a very high pressure on this main piston. We have here the pilot valve system here, that is a movement. So here this will be going down, means that is your change in XE position will come down, and finally it is, if going down this position, means it is opening and the more power or more steam is passing through the turbine. Thereby we are increasing the output of the turbine, and finally we are increasing the mechanical this electrical output of the turbine. So this is one way that various linkages, various positions are changing by change of even though one condition. Similarly, we can also see the speed governing system approach. So in this condition we saw that if we are giving the raise command, this only I talking, that we are increasing, we want to increase the power output of the alternators, and here if raise command is given, means we are changing the position of A. Now if we can assume that the change in position, just I want to write this XA, change in position B at the point XB, that's I can say this XC, here change in your XD, and here change in XC, means we have this 5 linkage mechanism. So what is movement for which linkage that is can be related by plus and minus, so that we can model later on, we will see how it is useful. Now if I will take the downward movement as positive, it's no problem, you can take as negative. So here it is better to understand that because we are increasing the power, so it is always better to take the downward movement as a positive. So here what we are doing, if you are giving the raise command, so the movement A is the downward. Positive value shows that the movement of that linkage will go down. Negative means it will go up. So here, as I said, A will go down. Now the B, as I said, it is not here speed governing system, we are not taking into consideration. We are assuming this is a constant, this linkage is fixed. So what is happening? Your change in position B is 0. Means it is not moving at all. Now if it is A is coming down, C is going up, means here C position that is changing upwards, and that it is against our convention. I said that if position movement is going down, then it is positive, if it is going up, it is negative. So your XC here will be negative. Now your XD is also going up, that is your also negative. However, the movement of your XE is coming down due to this pressure, it is your positive. Similarly, if we are giving the lower command, means all here just I have written for the raise command. So if you want to similarly to understand that, if you want to give lower command, means you want to reduce the output. So here what we can do, here this the sign of the various positions will be changed, and finally we will see here the A will go up, means it will move up, so it will be negative. B will be 0, there is no change in the position. The position of C now it will be going up, C will be coming the positive. Here your D will be also positive, and your E will become negative, and it will try to open. So this is for your lower command. So this is the change in the position. Again, I am not writing how much magnitude it is going to. It depends upon the several factors. It will depends upon the length of the linkage. It will depends upon that how much it is regulated. So it will be decided later, and the several constants are coming into the picture. So this is basically which I explained for the if you are giving raise or lower command to increase the output or to open this steam valve. Now let us see that here the frequency of the system has gone up. Means here the frequency omega, or you can say omega is directly related with that. So if this has gone up, then what will be the position of this various linkage? Again, I'll try to write here XA, change in your XB position, change in your XC position, change in your XD position, here D, and here change in your XE position. Now let us see, here now we are starting from B. So what is happening? We are assuming that here A is not changed, because we are neither giving raise or lower command, it is fixed to its rated value. So there is no change in position A, so it will be 0. Now the B position here if it is a speed is increased, what will happen? This spring will try to extend and it will try to reduce your XB position, and here it will be your positive. Means if your frequency is reduced, then this spring will try to close here, and here it will go up or going down here depending. So the change in XB position is directly proportional, I can say it is some constant with the change in frequency. So if frequency is more, this is a positive. If frequency here is less, so then it is a negative. Now if this is here is kept 0, XB, change in XB, it is a positive, it is going down, then your C here if it is going down, this will also going down, because whole this linkage is taking A as a center. If C is going and B is going down, C will be also going down, and then it will be, I can say, now the movement is in the positive direction, that is a downward. Now if the C is also going down here, now what will be the D? D here will also be going down, and then here it will be your positive. So if the D is going down, what does it mean? You can see if D is going down, this pilot valve will move down, and this high pressure aisle will try to move here, and it will try to insert a pressure on the main piston, and this piston will try to lift the position of E upwards and try to close, and then here it will be your negative. So what is happening, that the position of E is going upwards, means it is the closing of steam or input to the turbine, and we want that if here the frequency is more, means the input to the turbine must be reduced, and that we are achieving here. So this is the linkage mechanism. We can also write for the reverse case. Reverse case means if your frequency here is falling down, and then we can write what will be the position. I'll let you know. Let's suppose your frequency here is reduced. So again your change in A is 0. We are not giving raise or lower command. So the position of A is, change in position of A is 0. And now here B will be going up, that is it will be your negative. Once it is going up, your C will be also going up, that will be negative. If this is going up, your D will be also going up, and that is your here negative. If this is going up, what will happen? Here you can say now the oil pressure will come here, and this will be position will be E will be going down, and it will try to open the inlet to the turbine, and more steam or water, or you can say input of the turbine will be increased, and then finally then will be more, and then we can increase the frequency. This can be here summarized again in this here the case 1, just I have considered 2, and based on these 2 cases I'll just write the equations for this governing system. Already I explained the speed changer is given the raise command, and the speed is constant, that is here, that is omega is constant. So we can have these changes in the positions. Again here the positive movement is the movement in the downwards, I have taken as a positive. So change in A, if we are giving raise, so it is positive, no change position in the B because the speed is constant. C will go down, up, D will go up, and E will be going in positive direction, that is downward. So if speed of the turbine has gone up, that is omega has increased, and your this raise or lower command is fixed, it is not given. So the position of A will be 0. Now the B will be, frequency has gone this, so B will be going down, C will be going down, and here D will be also going down, but this will be going up, and it will be trying to close the input, and the frequency of the system will be restored. Now with these 2 cases, what we are going to do, we are going to model this governing system. Means you can see your change in the position here, that is change in position C, is nothing but change of the 2 things. Means the position of C is controlled. If you will see this figure here, change of the position C is related with the change in here as well as change in B. So the position A is changed by this command, and that is nothing but changing your power reference. That's how much power just you want to change. And another, that is a P reference card, and another is a system frequency. So these two change position is directly related, that is changing the position of C. Now you can see here, and I can write this position of the C is the summation of some constant. Again, the change in the frequency with the some constant K1, this is giving the position of C, minus K2, change in position of the C, that is a reference value. Why it is minus? You can see that we have the two options, that the change in position here, simply you can see the linkage mechanism. So this is your A, this is your B, this is your C. Now if you are changing this, means if it is moving in the positive direction, this is fixed, then this is moving in the negative direction, that is oppositewards. So that here if you are changing more power, this term is negative. However, if your frequency here is your increased, what happens? This is going down, here this is a constant, this is also going down. So here this is a positive. So the position of C is directly related with the change in the system frequency. However, the position of here the C is here the reverse of this position of A. So we have written the change in the position C is a function of the frequency and the change in the power, that is a PC. It is nothing but change in the PC is equal to your change in the P reference setting. So we can write the change in the position C is a function algebraic equation in terms of K1 and K2 constant, and these depends upon the length of arm. This one is moving how far it is, so it depends upon the movement. So these are the constants, and basically once it is desired, that K1, K2 can be obtained. So this is equation 1. Another, that we have this position of XD. XD is also here is linked with the D, that is the D position, and we can see this XD position here, if the C is going down, D will be also going down. So here the change of position XD is the related with the position of here is here C is D, and here let's suppose we have E. So if D is here going down, means here the both E is going down, then it will go down, and if here both are going up, it will be going up. So it is a combination of the change in the positions of C point and the E point. At the same time, the change in the E position, it is with the negative to the XD position, and that is the integration here of the change in position. Why it is so? You can see again with this help of this diagram. Now what happens here? Earlier it was moving up. Now what is happening? If it is moving up, you can say now the aisle pressure is coming here and it is going down. One way, if this D is moving up, E should move. But by moving this here, the aisle pressure is coming here, it is trying to reduce in the negative direction. So this movement of E here is directly related with the XD and with the negative direction, means if it is going up, it is moving down. But at the same time, here this is aisle pressure is there, and it is a continuous movement. It is taking time, because here the some piston mechanism is there. How much time it will be traveling here to the its settled value, means the pressure is equalized. This pressure and this pressure must be equalized. So it will take time, and that's why it is a integration time that we have considered. And that here we can write that is the XE position is with the negative, means opposite direction of XD with the integration, and that is related with the time. So the coefficients K1, K2, K3 and K4 are the constants and depends upon the length of the arms. However, this K5 depends on the aisle pressure, geometric of orifice, and the cylinder of your the piston valve, as well as the orifice of your the main valve system. So how much pressure that is going to equalize. So the K5 depends upon that. Now if we can define the constant K2, K3 divided by 4 is kg, and it is normally known as the static gain of governors. And similarly 1 upon K4, K5, that is a Tg, that is called the time constant of governor. So with these we can derive an equation in this, you can say, Laplace form, and here if we are taking the Laplace of these equations, means I can write here the change in xcs taking Laplace. So here it is nothing but your k1 change in your frequency, that is here now I can write the capital, that is change, minus your k2 change in your PCS. Similarly, I can write here your change in xd, yes, that will be equal to your k3 change in your xes plus your k4 change in your xes, and your xes change again is equal to minus k5 here change in xds, and here divided by s because it's a integration. So what we can do now here, by simplifying these three equations, we can have a relation between this xe, because xe is directly giving this input output, how much it is a orifice is opened of the steam. So we can simplify, means we can put here xd, xe here we can put here, and then we can get a relation between xd and xe. From here xd we can put here in this equation, we will get this change in your xe, yes, that is a function of, again no doubt, your change in fs and your change in PCS, and that you can see we can get this expression here. Here this k2 upon k1 is normally known as R, and that is nothing but it is your regulation of speed governor or droop value, or droop is very very important, this characteristic, the k1 k2 upon k1, that is R. This is basically related, we will see later how R is very very useful to control the frequency of the system, because this is the characteristic of the governing system, who is taking part and how much output is changed. Basically this R is the very valuable criteria. However, the Tg, that is the time constant, putting all the constant and simplifying, we can get the change in xe, yes, in the Laplace domain, that will be equal to your kg, that is the gain of the governor, over 1 plus the Tg, that is a time constant, multiplied by the s, and here we are getting the change in Pc minus change in the frequency Laplace divided by R, that is a regulation of speed governors, or the droop value. This equation can be represented into the block diagram, and the block diagram you can see here, this is your block diagram. So this block diagram basically you can see here. So what we have done, this change in the frequency divided by R, this is 1 upon R, that is coming here. This Pc is positive, this is negative, and that is multiplied by this governor block diagram, you can say transfer function. It's very well, that is the input output relation in the Laplace domain is your transfer function, and this is giving your change in position in E, and this change in position is directly related, that is nothing but change in the wall power, means how much is changing, so it is wall power is coming. Normally this Tg is 0.1 second here, and the gain again depends upon different criteria, and also depends upon k2 upon k1. So this is basically the model, or you can say transfer function model of the governing system. So this power, that is wall power, means we are changing the input to the turbine. So we have model, this is your raise and lower command, means how much reference you are changing. This is the frequency related component that is coming here, and the governing here, that is the opening or closing your valve, and this is going to your turbine. So the turbine, you can see the turbine here, that is we can model like this. So this is the which is coming here, it is nothing but change in terms of PCS, and then this turbine is giving some output, and that output is going to in terms of rotation, and then we will see here how it is related in this model of this turbine. So this is basically turbine. So this valve, which is the not PC, it is V, that is valve power, that is coming here, and it is going in this way. So now we require to model this. Because before that we have already modeled. We model complete the governing system. Now we are modeling the turbine system here, and the turbine model again depends upon the which type turbine we are going to use. It may be your steam turbine and it may be your hydro turbine. For example, the nuclear power stations, they also use the steam as a energy transfer medium. So the steam turbines are common. Again, slightly deviation that which type of steam turbine we are using. So the hydro turbines are very simple. However, these steam turbines may or may not have the reheating facility. So we can have the reheating facility or we cannot have the reheating facility, it depends. So then we'll have the different approach. For the reheating means again what happens if the steam is coming here. For example, if you are having the different stages. For let us see, let's suppose this is your turbine. This is your HP, that is a high pressure turbine, and now it is connected with your IP, that is the intermediate pressure turbine, that is your IP, and then you will have here your LP, that is a low pressure turbine, and finally you have your alternator. So this is a diagram. I can say this is LP, IP, that is intermediate pressure. So here steam is coming, steam is expanded. So what happens, this steam which is coming out from SP, here basically this is your boiler, let us suppose. So here from boiler it is coming, then this is again reheated, means it is going back this steam, and then after that it is coming to IP, and from IP outlet it is coming to LP, and then finally here it is collected and it is going again to the boiler. So this is a steam diagram. So what is happening here, this SP, the exhaust of, that is the steam which is coming out of the SP after doing the work, it has a very less temperature and the pressure, and there is a chances that the blades of these turbines, which are very very expensive, will damage. So what we do, we send it back to reheat. So what happens, it will take some time, means it will be going here and then it will be coming and then finally it is going to SP. Again we will see in the modeling. So what I can say in this module, first lecture is devoted to the modeling of the speed governing system. We model this in terms of Laplace transform to analyze the performance of the speed governing system, or you can say load frequency control. That is very very important. So here I just represented the block diagram for the governing system. Now the next is the turbine model, and we'll see for the turbines we can either we are having the steam turbine or hydro turbine, or sometimes for analysis purpose we go for the very simple model of the turbine, and that is used. So this turbine model will be discussing in the next. Here with both reheating and the with and without reheating facility, I explained what is the reheating, means the steam which is coming out from SP is reheated before passing to the intermediate pressure turbine, then it is called reheating, and due to this the travel of steam is coming here, so some time delay is involved, and we'll see the power output of these two, how it is related. Thank you.